Welcome to this tutorial for students studying Specialist Mathematics, Unit 3 in Queensland. In this session, we'll cover a range of topics including complex numbers, matrices, vectors, and along the journey we'll do some examination tips. The questions have been selected to highlight a range of ways that you can use the TI-84PlusCE to explore, calculate and verify answers in typical exam-style questions. If you're watching the recording on YouTube, you can download the question sheet using the links below. And please feel welcome to leave some questions in the comments section. So let's get started. In our first question, I'll attribute this one to Archimedes. We'll do a little bit of a background. Archimedes was a mathematician, a physicist, astronomer, engineer, inventor, range of talents. And he was particularly interested in circles and ellipses, possibly because his father was an astronomer. So, what's with the question? Archimedes invented this thing called a Trammel. It's a device that can be used to generate the shape of an ellipse at point P. You can see a diagram for the Trammel on the side of the screen there. And blocks A and B move backwards and forwards, and a rod connects them and has a pen or scribe, if you like, at point P. And it's point P that is tracing out the shape of an ellipse. And that's where our question is focused. So, in our question, we're given some information that block A oscillates according to the equation 10 sine pi t on 10. And block B oscillates according to the equation negative 10 cos pi t on 10. We'll assume, obviously, that the centre of the Trammel is at the origin. So the x-axis running through block A and the y-axis running through block B. Distance BP is fixed, as I said earlier. It's a rod from A through to P. It says that BP is fixed at 10 centimetres. There it is on our diagram. And time is measured in seconds. So we've given all our parameters. So let's have a look. What's our first question? It says, show that the distance AB is fixed and hence determine the distance AP. Well, the fact that our question says that we need to show it, that means you'll need to do some by-hand calculations. We can see that there's a triangle and that it's a right-angled triangle, and the x-axis, that length, is given by 10 sine pi t on 10, and the y one is given as negative 10 cos pi on 10, pi t on 10 rather. And we could use one of Archimedes' predecessors, Pythagoras, to show that distance AB is fixed. So there's the mathematics we're doing on that one. Fairly straightforward. We can take out a common factor of 10, and we can see that sine squared plus cos squared. I've replaced the pi t on 10 with theta just so you can identify the identity involved, and we get it simplifying to 10. So this is an example where you won't use your calculator to show, but you might want to check your answer. We've got 10 as our distance. So let's see how you might check that answer using your calculator. I'm going to put my calculator in parametric mode. So at the moment it's in function mode. I'll go across to parametric. And I'm also in radians because the movements of block A and B are described in radians. I'll press y equals. I've got some equations in there already, so I'll just clear those off. And from memory, let's see if I can remember what my equations were. I believe that the equation in the x direction is 10 sine pi. Now I could put these with a vinculum in there. I'm not going to bother because it's a fairly quick and easy equation to enter. And in an exam, you'd want to consider whether or not you need the vinculum. At times, it's worth it, particularly if the expression in the denominator is more than just one term. So, pi t over 10. So that's what we've been given. and I want to check the distance and show that that distance is constant. So I can simply do this, the square root of, and I can pick up my variables, my x variable, or rather the parametric variable, x1, and I'll square that. And I also need to put in my y value. And I'll square that. And I get 10. Now it's interesting because I haven't put a value in for t. I could double check it. I could put any value in I want for t. Let's just store that as 5. And you'll notice when I press x, t, theta, and n, it automatically defaulted to t. That's because my calculator is in parametric mode. I'll go back and I'll get this calculation, and it's still 10. So it's a quick way of checking to make sure that your calculation that you did in your show that is correct. All right, let's move on to part B of question number 1. Based on the direction of the arrows, in which direction is point P moving? So we see that block A is about to move to the left, block B is on its way upwards. So you could draw some diagrams, and depending on the amount of marks this question is worth, it's something like this, usually only 1 mark, unless it's requiring an explanation. So how would I answer it in an exam? Well, I've already got the values of, or the expressions for A and B, those 2 blocks, in my calculator. So I could have a look at where does this thing start? So let's go back to the calculator and recall that I can pick up x1 of t. So I'm going to store 0 in t this time. And I'll just go back and get each one of those variables or those expressions and paste them in. So it says my initial x position for block A is at 0, and then I'll go and get the one for y1 of t, and its initial position is at -10. And then you could draw a diagram. Then go back and change this value for t. You'll notice that I'm arrowing up to go and copy and paste. So I'll just draw it as 2, just some arbitrary value. So I know 2 seconds later, whereabouts will blocks A and B be located. So I've got an x coordinate and a y coordinate. So then you can draw a diagram to sort of get an indication of which direction P is going. Well, it's a bit hard to draw on the screen, but I've got an animated diagram here that I can use. This is my Archimedes Trammel. And if we recall, block A said it was at 0 and block B was at -10. And then some 2 seconds later, we can see that A was positive and block B was still negative. So we can see that point P is moving in a clockwise direction. If I wanted to, in this diagram, I could even fast forward it to the time represented in the diagram. So that's where block A is moving on towards the left and block B is still moving upwards. And of course, P is still going around in a clockwise direction. So you could support your answer depending on the number of marks that it's worth. You could support your answer with some calculations, or if it's only worth 1 mark, it's only asking whether or not it's moving clockwise or anti-clockwise. Right, part C. How long does it take point P to complete a single revolution? Well, I could do it from my diagram and just keep on circling around there. But on the actual TI-84, if I wanted to draw a graph, I've got the equations in already, but watch what happens when I go onto the window settings when I'm in parametric mode. It says T minimum equals 0, T max equals 60, and I've got some values down here. I'm going to put these as -10. Actually, I'm going to bump that out a little bit, -15. and 15. And I'll do y with similar sorts of values. We're going to play around with this for a moment. If you've never used this mode before, I'm going to leave the T max at 60 just for fun. And I'll press the graph and I can see I get an ellipse, but that's not really what I'm looking for. Because it's not really an ellipse. That's because my window settings are not square. So need to be careful of that. So I'll go zoom and look at that. Option number 5 says zoom square. You'll notice that that thing went around a couple of times if you're watching the screen carefully. Well, we know from our formula for the period that we should get a period of 20 seconds. So let's see, if I wanted to check my answer using the formulas, if I change that back to 20 seconds, now did it complete one full revolution? If it did, then changing my time value, my T max to 15, should just produce 3/4 of the circle, and it does. So this is another example of me just using the calculator, other than the trivial calculating the time period. It's also using it to check, are my calculations, is my theory correct? Does it complete one full revolution? And if you wanted to be a little bit clever, we can also plot those blocks. This is just being a little bit cute. It's not something you'd want to do in an exam unless you're finished and you've got to fill up some more time, I guess. I'm going to put in the equation that we had for the y value. I'm putting in x2 and y2 this time. So if I put in negative 10 cos pi t on 10, and not sure if you've ever seen this before, but you can go in here and you can change the sort of line that we're doing. I'm going to have a little bubble on the bottom, which is going to kind of make it look like the blocks. So what's the difference this time? There's block A oscillating backwards and forwards as per our description, but where's block B? The problem we get here is that the calculator is doing the graphs one after another. It's doing them in a sequence. So you can go into your mode settings and go down, and instead of doing the graphs in the sequence or sequentially, you can do them simultaneously. And watch the difference this time. Now we're seeing block A move backwards and forwards in a horizontal or the x direction, and block B going up and down in the y direction. And if you imagine block A and block B connected, we're getting something close to what you saw in my animation before. And we'll see that after 20 seconds, both blocks have completed one full oscillation. All right, that was a bit of fun with question C. Question D, determine the Cartesian equation for the ellipse. Now that's an interesting question because we're given this equation in parametric form. Now, we're kind of given a hint to this at the start with block A and B being a constant difference. We can see that the result is an ellipse, where the longest radius would be 20 and the shorter one would be 10 because it fits neatly around the Trammel. But I've got a diagram here that might help. So that's what we've got in our question, and we can see it moving around. If I want to see more of the reason of why, I put some arrows in here. So we can see that in the x direction, so the location for point B is just the mirror image of where A is located. It's being flipped around because of it's attached to block B. So in the x direction, let's go back to our calculator and we can type that in. So down here, for x3, I'm going to put negative of whatever is in x1. Now I could retype the equation, or I could put in negative x1 of t. I'm just going to put in negative x1 of t. Let me see, negative 10 sine I t over 10. That's our first one. This is for point P. Now, the y direction, we can see that it's got this component, which is exactly the same as what we're given for the location of B, but it's been extended. And remember in the question it said BP is fixed at 10. You should be able to see some similar triangles in this that relate this triangle here to this one here. So in actual fact, because this distance is 10 and that distance is 10, I can shortcut it. I can say that it must therefore be negative 20 cos pi t on 10. Now, if I draw the diagram and do my graph, it's done. I'm kind of missing the top bit though. And we might want to zoom out a little bit. Now I can change all these values, or there's a zoom option. You can see you can zoom out. I might not want to zoom out too far. Not many people have used this option, and this is something you'd set up before your exam. What sort of factors do you want to zoom out by? So option 4 to set factors, see the zooming out by a factor of 4, that's a long way out. You might want to change them to 2, or in my case, I'm going to change the zoom factor to 1.5. Now your calculator remembers these factors. So now if I go zoom and then zoom out, centered at the origin, and now imagine the line is connecting the blue point, the red point, and hitting point P. Unfortunately, I can't draw that in on my 84, but you're getting the general idea. And my Trammel seems to be progressing quite well. So, now that I've got my parametric equations, I can get the Cartesian equation. There's a little bit of work. I'll let that animation run on in the background. So we've looked at the location when t equals 0, and also at t equals 5, because you don't always have to come up with a parametric equation. You could have come up with the equation for the ellipse using the Cartesian equation of ellipse just by picking up some points. But if you're using the parametric equations, the two that I've just created, there's our Cartesian equation. That's obtained by dividing, in the case of x, dividing by 10 or negative 10, and in the case of the y direction, divided by 20, and then again, using our trigonometric identity, sine squared plus cos squared equals 1, so I'll get x squared on 100, y squared on 400. There's my parametric equation, my Cartesian equation for the Trammel. Part E. Describe the speed of point P as it transcribes the ellipse, including the maximum minimum values. Now, this is a question where you'd really want to have a look at how many marks is it worth, because describing the speed of it might be a literal interpretation. So if the question was worth 3 marks, you'd probably be getting 1 mark for your description and 1 mark for the minimum speed and 1 mark for the maximum speed. If, on the other hand, the question was worth a few more marks, say 5 or 6, you probably want to be putting in an expression or an equation for the description of the speed. So we've got a bit of work to do here. I'm going to do most of it on the calculator. I've got an equation or an expression for the position x1. So if I come down to here, the speed is the rate at which this thing is moving. So I need the derivative of this expression here. Using the math template, there's an option for a derivative. And mine is with respect to t. And I need to differentiate the expression in x1 of t. So let's pick that one up and paste it in. And I need that for all values of t. The other thing I need to differentiate is the expression in y2. So same as what I just did, chance to practice it. Numerical derivative with respect to t, that is time, for all values of t. Now the question asks for the speed. To calculate the speed, rather than velocity, it's the magnitude of these things. So I can do x4 of t, square it, and add in y4 of t squared. So I've got my speed in the x direction squared plus the speed in my y direction squared, add them together, square root them, Pythagoras again, and that will give me the speed as this thing progresses. So you can see it's drawn the graphs of the speed, not particularly useful, except if I want to calculate the speed, let's say at t equals 0. If you're doing that by hand, you'd need to do the derivatives of xt. That's all I've done there, set those up. So we do the derivative of x of t, the derivative of y of t, and our speed is given by the square root of the 2, which is what I just put in. And that simplifies to that. Now I can get those from the calculator, or I can substitute values in. Hopefully you can see that when t equals 0, we'll get sine squared will be 0, so we'll get 1. And the maximum is going to be when sine of whatever it is equal to 1, which will give us a maximum speed of 2 pi. So minimum speed is pi and maximum speed is 2 pi for the motion of p, which we can get. The trick with this, again, it's another question where you need to know a little bit of mathematics before you can even enter it in on the calculator, because you'd need to know where are those maximum speeds occurring rather than trying to use a solve. All right, next question. It's time to do some complex numbers. So given that z equals 2 cis pi on 6, determine the value of z to the 7. Now you'll notice that there's no cis command on the calculator, but there's a tip here. That is, r cis theta is exactly the same as re to the I theta. You'll notice that most electronic devices tend to use re to the I theta. R cis theta is very visual. Re to the I theta is a much more elegant way of representing things in electronic formats. So I'm not going to bother to try and write it as r times cos of theta plus I times. I'm just going to use this representation over here. It's much quicker. So we've got 2 cis pi on 6. Now obviously this one's asking for us to use DeMoivre's theorem, but on the calculator I can put in 2. Let me just double check it. Yep, 2e to the power of pi I. Now, make sure you use the complex number I. Don't use the letter I. Over 6. And you'll see that it writes it as 1.7. So it writes it back in rectangular form. Why does it do that? Because if I check on my calculator, it will default to rectangular form. But if I tell it to write it in that form, in this polar form, it'll leave it in our cis format, or RE to the I theta. So now if I go back and just press enter, you can see it's leaving it in this form. But we need to calculate that value to the power of 7. Now we've got a problem. We've got this really unusual angle, and it's not an exact value. So how do I get that as an exact angle? In the complex numbers tools, I can grab the angle, number 4, of this expression. Not useful, it's just writing the same as what I saw in the exponent, except we suspect this is some multiple of pi. So if I divide that by pi, and then times it by 180, in other words, convert it to degrees, I'm reasonably confident that my angle is minus 150 degrees. Now, one of the advantages of this is that we know that the argument should be expressed between negative pi and pi. So therefore we can state that the answer is negative 5 pi on 6. And if you wanted to, you could test negative 5 pi on 6 and compare the result to negative 2.61799. I'm confident we've got that one right. So our answer would be 128 cis negative 5 pi on 6. Question 3. Another one on complex numbers. Which of the following is a solution? Now this one's a little bit challenging because there is a polynomial root finder on the TI-84, but it doesn't cope well with having imaginary coefficients. But let's remember something. This question's actually given us the answers. We just have to figure out which one is correct. Now that might seem a little bit silly. So I can actually type the expression in, this z squared plus 6iz minus 10 equals 0. I can type that into the calculator. Now, you could just let it equal 0 and just find out what each of these things results in and pick the one that equals 0. I'm going to use another feature called the test feature. So I'll start by typing in z squared plus 6 times I. Again, make sure you use an imaginary number I, not the letter I, minus 10. And then I'm going to write in test equals 0. Oh, didn't like that one. Maybe I'll leave it off. Didn't like my test equals 0. So what I want to do now is I want to substitute values in for z. And one of the first options that was presented to me was 2 minus 3i. So I can go 2 minus 3i, and I'll store that in z. Now all I need to do is go back and get the original question. It says the answer is 3, which is not much use because I need an answer of 0. And now I don't have to retype everything again. Oops, too far. Option B is the same as this, but with a plus sign. So now I can go back and check. Still not getting a 0. What other options do we have? 1 minus 3i, 1 plus 3i. So I'll go back up to here. And we'll type in 1 minus 3i. Now, the interesting part about this is you may then think, oh, but what about 1 plus 3i? Because shouldn't the conjugate be a root as well? And the answer is no. The conjugate will only be a root if all of our coefficients are real. Because I've got an imaginary coefficient, and we'll just check it to prove that 1 plus 3i is not a solution. You can see there it doesn't equal 0. So our answer is 1 minus 3i. So that's just another way to substitute values into an expression. Of course, you could have factorized it. That would have been another way. Some students might struggle with the 6i and the factorization part, but you should be able to do those things by hand. So you can see you can use the calculator to find a solution as well. Question 4. Now, it looks almost exactly the same, and we could approach this the same way as what we did before, but sometimes you shouldn't use the calculator. In this case, as long as you understand what's going on, you should be able to pick the answer out of there, knowing that there's only one correct answer. So if I substitute that into there, there's a bit of calculations I'm going to have to do. I've got a 3 and I've got a minus 3, so they'll scrub each other out. And I've got a minus 3i and a plus 2i will give me a minus I, and then I've got to take the magnitude of that, which will be 1. So I don't think it's the first one. And option B looks as though it might end up with something very similar. But let's scroll down. So you can go through exactly what we did with question 3. But if you have a look at option E, look what happens. If I put z equal to negative 2i, it cancels out, and I'm just left with the magnitude of negative 3, which is 3. So the answer is 3. It's much quicker. So in question 4, what we're trying to show you is that just because you can use a calculator doesn't mean you should. There are times when it's quicker to do things by hand. But at the end of the exam, if you've got some time left over, by all means, come back and check question 4 using your calculator. Okay, question 5. This one's actually to do with matrices. Now, there are a range of ways to solve simultaneous equations on the 84CE. I'm going to use a matrix because there's a really cool command called row reduction echelon form. So let's see. Now, I know we're almost out of time for this session, so I'm going to show you another little trick. Here's one I prepared earlier. On the calculator, there's this thing called the group file. Out of the memory option, you see option number 8 is group. And I'm going to ungroup something which coincidentally I called question 5. And it says this involves some matrices. Are you okay to overwrite them? I'll say yes, please. There's no speech recognition, so you'll have to press a button and not say yes. And now if I go into matrix A, let's have a little look. Oops, clear. Let's have a little look at what matrix A looks like. That is indeed the coefficients 2, 4, and -1 of x, y, and z respectively in the first equation, which is equal to 12. Let's go back and have a look at that first equation. 2, 4, -1, and 12. 2, 4, -1, and 12. -3, 2, 4, and 4. -3, 2, 4, and 4. And the last one, 5, 3, 1, and 5. 5, 3, 1, and 5. So what do I do with that to solve those equations simultaneously? Under the matrix command, in the math section, scroll all the way to the bottom. I just hit the up arrow and I'll select row reduction. I want to do row reduction on that matrix. Oops. Matrix A. And that tells me the solution occurs when x equals -0.637, y equals 3.06, and z equals -1.01. I'm done. So that's solving a set of equations simultaneously. And the last question. one on matrices again, Leslie matrix. That initial population, that Leslie matrix L, there it is there. It represents the population of a series of rats, female rats, and the initial, well, that's the transition matrix, sorry, and the initial populations for the rats 10, 6, and 4, these rats live for 3 years, and they're divided into the 3 age groups. The first age group being young rats, there's 10 of them. The second age group being juveniles, of which there's currently 6. And the last one being the adults, of which there's currently 4. Now, Leslie matrices are used often to look at the way that the population is growing and evolving, the proportion of young rats that will be present in 5 years or 10 years or 20 years' time. Will they die off? Will they go into an explosion of number of rats in the world? So, let's have a look at our first question. It says, what is the probability that a juvenile rat reaches adulthood? This is not a calculated question. This is just, do you understand what the Leslie matrix is telling you? The number of rats that transition into adulthood is given by this line here. So, the juvenile rats, 0.2 times 6, and the junior rats, the baby rats, 0 times 10, they don't contribute to the adult population in the very next transition. It's only these juvenile ones, and then 0 adult rats turn into adult rats in the next generation. That's because our rats only live for the 3 generations, the 3 transitions of 3 years. So our probability is simply 0.2. No need to use a calculator. It's just, do I understand the Leslie matrix? This one, on the other hand, I think I'll use a calculator for, because that's going to be really hard. How long will it take the female population to pass 1,000 rats? So, again, because I'm getting tight on time, it's one I prepared earlier. Watch this. I'll grab question 6, and all I'm doing is populating some matrices. So let's have a look at matrix A. Oh, I'm going to do it again. I almost forgot to clear it. There we go. So, matrix A, that's the Leslie matrix that we have. And matrix B, that's our initial population state. So I can see how many matrices, how many rats will be present in the next generation by multiplying those two. So there'll be 24 baby rats, 4 juveniles, and 1.2 adults. That's an interesting number of adults, isn't it? Remembering these are approximate calculations here. So I need to find out when the population is going to exceed 1,000 rats. So I could sit there and do that time and time and time again. And the total number of rats is 28, and one more is 29, almost 30 rats. Seems like I've got to add these up. Well, you might have noticed that I added an extra matrix in here, which was matrix C. If I do matrix C multiplied by that, I'll just get 1 times that, plus 1 times that, plus 1 times that. It's going to add them up for me. So it's kind of a neat way of doing that. So let's do this. Matrix C times, let's see if I can paste these values down, the thing I typed in before. And you can see it's just added them up for me. Now, nice thing about matrices, if I want to repeatedly multiply by that transition matrix, all I need to do is go back to this one, and I'll change my cursor to an insert cursor and put a squared sign there. So that would be 2 generations. We see we get 48 rats in total. I can go back and paste it. We're nowhere near our 1,000, so let's try 20 generations. That's a lot of rats. wonder if we could do 10 generations. Then in a moment, we're just doing a guess and check. I've still got more than 1,000 rats. Is there another way I can do this? Well, I can't graph a matrix. So our last trick for today is this one. Is this thing called the determinant. That returns a numerical value. So I can close my brackets and I get 3,000. Notice it's no longer a matrix, which means if I go into here, not the parametric mode, I'll need to change my mode back to function. And let's put all of that stuff in here. Man, it'd be nice to have copy and paste right now. So I'll take the determinant of matrix C times matrix A to the power of X and times that by matrix B. And we'll set up the window dimensions. We'll go from 0. We can see that 10 was already too high. And a scale of 1 would be good. And we'll set the Y minimum as 0. The Y max can be 1,200 rats.
Now I'll set the Y scale at 200 and the X resolution at 1 and delta X at 0.05. You'll notice that changes our X max, but it allows us to do a much better trace. So we can watch our graph slowly generate. It's discrete because of the individual steps. You can also have a look at this as a table of values. To do that, let's have a look at the table settings so that we can increment them in steps of 1. That is our delta table. And now let's have a look at the table of values.
Now you can see I've got more than 1,000 rats. So you can see this is actually a quick way of jumping through those calculations. Rather than trying to do a solve, which can be a bit messy, I can see after 7 generations, I've got 686, and therefore at 8 generations will be the first time that I see so many rats, 1,000 rats. And part C for this question looks at culling off the rats because nobody wants to see that many rats. We want to reach a stable population of rats. So the stable population is looking at what happens in the long term, and that can give us the rate. So if I pick up my Y variable, I'll pick it up a different way this time. If I go alpha, F4, you can see I can pick up my Y variable. And let's do 100 generations of these rats. That's a lot of rats. Let's do 99 generations. So if I get those two values, I get an approximate rate, or ratio if you like, for the increase of the rat population. So in successive generations, it's increasing at a rate of 1.695 times the previous population.
This is called the eigenvalue. So if I do 1 minus the reciprocal of that amount, that will give me the Cull rate that I'm actually looking for. That is the proportion in each time period that needs to be eradicated in order to reach a stable population. That also means that 1 minus that value would give me the amount that I'm going to retain with successive populations. So if I want to see that stable population, I can go ahead and put that value, which I've stored in K, into my graph. Don't forget to raise it to the power of X for each time period. And we'll change our window settings up a little bit because I don't think I'm going to reach 1,200 rats this time. So let's swap that down to about 25 rats. Hopefully we've reduced the amount of rats that we're going to see. And the next, a y-scar rather of 5. And if I swap my step value back, I'm pretty sure it'll jump back to 13.5. And then I can see my graph showing the stabling of the rat population.
So that's all for this session. If you want to see more, then you're welcome to check out the education website, education.ti.com/Australia, and jump into the student section to see all the tutorials that we have on our TI-84PlusCE for students in Queensland. Thanks for joining us.